In episode 6, I told you that moving objects undergo contraction in space. This leads us to the following apparent paradox, which I dare you to solve.
Consider a cage whose width is Sheldon's height, but imagine Sheldon flying from left to right. In the frame of the cage, Sheldon is moving, so he'll be contracted and thus smaller than the cage. But in Sheldon's frame, it is the cage that's moving and that's thus contracted. We seem to have to conclude both one thing and its exact opposite. Namely, it seems that we both can and cannot put Sheldon in jail.
If we were doing quantum mechanics, I'd say, why not? But we're not doing quantum mechanics, and we need to fix this paradox. So I'll let you think about it while I dance to the sound of music. Time's up. Here's the answer. The answer is that it is relative. It depends on the frame of reference from which we're observing the universe. And the reason for this is that what we're asking is whether Sheldon's head is still in the cage at the instant where his feet have got in. In other words, we're asking about the simultaneity of two events, and simultaneity, well, that's relative.
To better understand, we should use the so-called Minkowski diagram. The x-axis represents the left-right direction, while the y-axis represents time. And since the speed of light plays a central role in relativity, we will convert the time scale into a distance scale by multiplying it by the speed of light. Thereby, if the y-axis is ct and if its unit is the same as the x-axis, then the light trajectory through spacetime will be inclined by 45 degrees. In this diagram, we can represent the position of light at any point in time, but we might as well represent all the positions of light at all times. We then see that the light will be a 45 degree straight line. Similarly, the cage and Sheldon corresponds to lines that represent all positions through time. In the frame of the cage is the y-axis, while Sheldon is a steeper line than the speed of light. In fact, since the speed of light is the largest possible speed, any trajectory will necessarily be steeper than the speed of light. In other words, the point of spacetime that an event can influence is exactly the cone inside the light trajectory. This is why we call this cone the light cone or the causality cone. If an event is within the cone of another, then there can be a causal link between them. However, two events that do not lie in one another's light cone cannot influence one another. In fact, what we're saying is that our spacetime has a maximal speed of causality, which turns out to be the same as the speed of light, but it is this maximal speed of causality that rules our spacetime.
Now I must say that there was a big mistake in what I've just said, and this mistake will actually lead us to solve the apparent paradox. Did you spot it? Our mistake was to consider that Sheldon and the cage were punctual objects, but they're not. They actually take some space. As a result, they should not be represented by a line, but rather by some infinite rectangle. In the frame of the cage, the left-right width of Sheldon's rectangle will be smaller than that of the cage. This means that when Sheldon's feet get into the cage, his head is still within the cage.
To now understand what happens in Sheldon's frame, we need to turn spacetime so that Sheldon's trajectory becomes vertical. But we cannot do this arbitrarily. Light trajectories must remain at 45 degrees. The only way to do so requires to turn the x-axis in the opposite direction as the way we turn the y-axis. This weird transformation is quite unusual, but it was perfectly well described by physicist Hendrik Lorentz a decade before Einstein. That's why we call it a Lorentz transform, even though Lorentz never derived the real contraction of space and dilation of time that Einstein would later understand. Anyways, once this transformation performed, we see that in Sheldon's frame, the temporal order of the events is inverted. His head comes out of the cage before his feet get in. Besides, we can draw slices of spacetime that the cage would consider to be simultaneous, and we see that these slices differ from Sheldon's slices of simultaneity.
Moreover, we can see that the fact that Sheldon's feet have got into the cage or not when his head hit the end of the cage does not really matter. And the reason for this is that the two events are not in one another's cone of causality. They cannot influence one another. So if you assume that Sheldon dies instantaneously when his head hits the end of the cage, then his feet will actually not know a thing by then. It will take time for the information to flow from his head to his feet, but by the time that this information has reached his feet, Sheldon's feet will already be within the cage. And this is why there's really no paradox in this setting, even when Sheldon crashes into the cage and dies. So we have seen how Minkowski's diagram helps better understand causality, contraction of space, and relativity of simultaneity. There's one thing left, which is time dilation. And to do so, we're going to slightly modify the thought experiment that we did in episode 6 by having the light beam going left-right rather than up-down.
In Minkowski's diagram, the space in which the light will go left-right is a rectangle. The edges of the rectangle will send one another light at a 45-degree angle. But as you can see, when the light is moving left to right, the right end of the rectangle is moving away from the light. This means that it will take longer for the light to bounce back than it would if the rectangle was vertical. Since the time between two ticks is greater for the moving rectangle, this means that moving clocks tick slower. If you now take any two events in spacetime, the straight line that goes from one to the other will measure the proper time it will take for a particle to move at constant speed to get from one event to another. As counterintuitive as it sounds, this represents the trajectory that maximizes the time it takes to get from one event to the other. This maximal proper time is the absolute measure one can do in our spacetime.
Conversely, this all means that if you're always going near the speed of light, then you can travel a lot of space with almost no time. If you're actually zigzagging, then you can go through a lot of time, according to others, without almost undergoing no time for yourself. By zigzagging near the speed of light, you can actually time travel to the future. Now that's pretty cool. Hey, so I hope you've enjoyed this episode. I don't have any future upcoming episode on relativity, at least nothing that's planned so far. So I'll just invite you to go again through all the episodes that I've made, especially about the general relativity, and I hope I'll see you there.
Things don't move through space-time.
So if we just rotate the slices of time while sliding them, then we can keep the speed of light the same and explain how things can move too.